here for letter C. The loop has a resistance R. So we're still looking at the 2004 AP Physics C electricity and magnetism exam for response question number 3 for inductance. We're looking at this loop. We just did part B and now we're on part C here. The loop has a resistance R. Calculate each of the following in terms of R, I naught, E, L, and fundamental constants. What is the current in the loop as a function of time? So, this isn't actually that bad. What we know, they just gave us that this loop has a resistance R, which means that we know it is going to internally generate an EMF due to the change in flux. And we know by Ohm's law that an EMF equals a current times a resistance, and this EMF also equals the negative change in flux in an amount of time. Remember, this negative here is just a convention as to what direction things should be flowing, which means what we can say here is that this current as a function of time is just going to equal 1 over R times the negative change in flux as a function of time. Luckily for us, we just figured out what that change of flux was in part A. We have an equation for flux here. It is equal to this. And what is also nice is what else can we do here? Oh, in part B. In part B, we know what I of t is. So what we can say what we can say here is that given that our flux is 4 mu naught IL over 2 pi, natural log of 4, instead of plugging in, here, let's just write this out. This is going to equal 1 over R times the negative d of, and then 4 over 2 is just 2, so let's just write this 2 mu naught L, and then that was I, and this is just over pi with a natural log of 4 thrown in. This I right here is no longer I. This I, we can now write this as I of t, because that's I changing as a function of time. Which means that all of this internally right here, we can rewrite as 2 mu naught L over pi natural log of 4, and then this becomes, the I of t is I naught e to the minus, what was this, kt? Yeah, e to the minus kt. We need to take the derivative of this with respect to time. Luckily for us, all of this here is a constant, so we could actually pull it out. We don't need to bother taking the derivative of it. The only thing we need to take the derivative of is this exponential. The derivative of that is just going to be minus k, because we take the derivative of the exponent with respect to time, so the t becomes, the 1 pulls down on the k, t to the 0 is just 1, so we get the minus k to the outside, e to the minus kt. So that's the derivative we care about, that we're going to shove in with all of the constants, so that this now looks like this. We're now going to have something along the lines of our current as a function of time is going to equal 2 mu naught L natural log of 4 times I naught e to the minus kt. And then there's the negative, how do I want to do this? Times the negative change in that flux has that negative k in front of it again. So this is just going to become a positive k in terms of that value that's pulled down. And then this is divided by the pi from this, as well as by r, which exists there. And that's it. That's a bugger. But that's it. A ton of constants in one quick derivative. It just was important to remember here that when we did this, we got a negative on this derivative, and whenever we have the flux, this negative is only there as a directional point, so we just, the two negatives worked against each other there. Okay? So not too bad. Not too bad. Quick derivative. Last but not least, when you get the total energy dissipated in the loop from t0 to t infinity. It is important to remember that energy can be thought of as how much power you're using as a time. Remember, work, which is energy, work, which is energy, can be thought of as a power multiplied by a time. And we want to go to infinity. So what we're really talking about is work or energy is going to be the integral of power from 0 to infinity here. We could write power in a number of different ways. One way we can do it here is I squared times r. And we know what that I squared value is as a function of time because we just wrote it above. This is going to lead us to a math nightmare, but it is what it is. It shouldn't actually be that bad because there's just a lot of constants there. So above, we had, if I can remember, 2 mu naught L I naught K, and then e to the minus kt, all over pi times r. All of this here is the current, I. So this entire value needs squared, and then we need to multiply this times r. So this right here is I squared, and that's r. Whew, okay, so not too bad, not too bad. We can work with this. Let's just highlight all the constants we're going to bring out. 2 mu naught L I naught K pi. Those are all squared. So let's pull them all to the outside real quick. So here is a 2 mu naught L I naught K squared. And then we can actually recognize that this is r to the first and this is r squared because it squares up there. So this r is going to go away, but I'm still going to have an r in the denominator that I'm going to pull to the outside because that's a constant. And the only thing I'm left with on the inside then is the integral from 0 to infinity of e to the minus kt. And I have to remember that value was squared there. So it's actually e to the minus 2 kt dt. Don't forget your dt. So I've got a ton of constants outside, and then one quick little integral to do, which isn't too bad. To take this integral, remember whenever you take the integral of an exponential, you take the derivative of the exponent and then divide by it. So if I take this exponent here, negative 2kt, and I take the derivative of that with respect to time, I get negative 2k, and then I divide by that negative 2k. So this is going to give me my big constant thing out in front, and then a 1 over negative 2k times, and then it's just the function, the exponential again, minus 2kt going from 0 to infinity. when I go from 0 to infinity for this bit here, this is really, since it's a negative exponent, this is really like saying 1 over e to the something, some number time. And when I go 1 over infinity, that gives me 0. And then when I subtract the second value, and I put the bottom in, and that is to the 0th power here, that's essentially saying 1 over e to the 0, which is 1. So I'm going to get 0 minus 1 for my upper and lower bound term out here. So the 0 doesn't do anything, and I'm just going to get a minus 1, which means that I'm going to get some stupidly big constant stuff. And I can just write this all out. The graders don't mind. I get a 2 mu naught L I K, all quantity squared, over R times the 1 over negative 2k, and then times negative 1. Whew. If you wanted to reduce this, we can. The negatives wipe. This is a 2 squared, which is a 4, and this is a 2 in the denominator, so I'm just going to bump this 2 to the outside. I've got a k squared and a k in the denominator, so that k is going to come outside, and those have gone away. And then at that point, do I have anything else? I could write this as 2k over r times the quantity of mu naught L I naught, if I wanted squared, if I wanted to. But honestly, I just end it up here. You're good there. You're done. It's all finished. Nothing too bad. So that was it. That was part C and D of this. The whole problem itself had a fair bit of calculus in it. None of it was actually difficult. In part A, we just had to integrate dr over r, which was a natural log, so we should be pretty familiar with that. We just had to be careful about where we started that. We had to start from point L and go to 4r, out at the edge here. In part B, it was just really a right-hand rule in explaining Lenz's law. And then part C and D, we had a derivative, not too bad, a ton of constants to pull out. And then in part D, we had an integral then of the power. But yeah, nothing too bad, just kind of an induction problem. We should feel pretty good about it, because this problem is finished. And thanks for watching both videos. Take it easy.